So having decided that we're going to go for the Riemann sum, and that within the Riemann sum we're going to look at, we're going to pick the midpoints, let's see what we come up with. All right, so the integral we're looking for is the integral from a to b of f of x, and so we're going to say we're going to approximate that with the sum from 1 to n of the value of the function at the midpoints of each of the intervals. So what we're doing is we're looking for the area under the function f of x. We're assuming f of x is positive. Usual provisos here about the integral and when the integral equals area and so on. But just to give you a visual representation of what we're doing is we're taking this region and we're slicing it up, and then for each of these slices we're going to pick as the representative point the one in the middle of each of the small intervals in which we have subdivided the interval from a to b. So what we're going to do is we're going to pick, for instance, in the first interval, that midpoint, which will be x bar 1, and then x bar 2, and then there is the rest of them all the way up to x bar n, since we're using n intervals. So do we have a formula for these xi's? Well, here is the formula. It's not pretty, but there it is. Let's see what this formula says. Well, it says start at A. If you're looking for the ith midpoint, you start at A, you move up by I times the width of each of those intervals. So that gives A plus I times delta x. Of course, that's too much because we have overshot the ith midpoint. So we go back by half of the width of the interval. Now we can rework that formula to make it look a little bit different. I don't know if you like this particular formulation. You may want to see if you have other formulations you can use. In particular, in a moment we're going to use the value of delta x as being b minus a, so the width of the whole interval divided by the number of intervals n. But again, the formula does not look particularly elegant, particularly easy, and so on. So you may or may not want to use a formal formula. And that's kind of a strange thing to say, a formal formula. But yeah, we don't want to use something that is too formal. So the midpoint rule says if you want to compute that integral or approximate that integral, compute this sum of the value of the function at the midpoint times the width of each of the small slices, and you can write that in this way. So delta x is going to be b minus a over n, and then we have the sum of the values of the function at a plus 2 minus I minus 1 over 2 times delta x. It's a pain to read that formula, isn't it? So my suggestion would be to actually work it out by hand, trying to understand what you're doing. Once again, if you really have to apply this formula for real, you'll probably rely on some computer program, and those will have all those formulas already included in them. But the idea is that what we're going to do is we're going to take our delta x, which is b minus a over n, and then we're going to multiply that by the value of the function of the first midpoint, whatever that midpoint is, plus the value of the function of the second midpoint. Here is another formulation, by the way, of that second midpoint, plus all the other ones, and then until you get to the last one, again another formulation for the last midpoint, and that's going to give you your formula. So it's a bit of work involved, granted. It is a numerical procedure, so it's not as elegant as the fundamental theorem, but when the fundamental theorem doesn't work, what can you do? You have to try some alternatives, plan B or C or D. We're going to look at plan C and D in a moment.